as we're pulling this up, so I'm Rich Ham. I'm the Associate Director of the MS and Operations Management Engineering Management Program, and have kind of had another role that morphed here that started 4 years ago with Dr. Swee's predecessor, and he, because of my background, pilot, and had done some things as a regulator in elsewhere again.
Jason, did you add this? Did you add Rich's?
Should be. Let's see here.
Anyway, Dr. Rankin, he called me in and he said, I'd like to have some help. He said, I think we have a couple of drones, and we're not sure, but we're thinking maybe this might get to be a big deal, so we might need a policy. So, no, we should probably think about it, but I think we have a couple. Could you track those and help them out? So we started looking, and about within a month, we found 16 drones on campus that various departments had purchased. And so that led us into a process. I'm going to use a use case of a recent project that we were involved with USGS to kind of talk a little bit about our process, and then what we do when somebody says, hey, I've got this, I think I might want to use a drone to gather some data. This particular one, it's Andy Lamb here at the university. He had called me because Jonathan Glenn from Menlo Park and USGS, a research scientist, had called and said, hey, we've got these big projects, we want to go out and measure some magnetic anomalies in a couple of places, primarily in North California and Southern Oregon. So we spent some time. They kind of knew what they had. There's only a few sensors that make sense, but the way to mount those sensors, basically what it comes down to is we're asking drones to do things they were never really designed to do. If you call the manufacturer, they'll say, don't talk to me about that, I don't want to hear about it, because we're doing some things that they were never really designed to do. So we spend some time on a process to look at that, look at the needs that whatever the researcher is, they say, hey, this is what I need to do, and they have some constraints that they'll introduce. Then we'll look at compliance issues, the platform, and how to design that to make that work. So I did this to just kind of show the team. This was an unusual one in that it's a very large area. One of the lakes is about 70 miles long, dry lake bed, that has these dikes and anomalies that are going throughout it, hot springs in both of them. I didn't get to go in the springs, either one, because we were working too much, but nonetheless, kind of a resort area in rural areas in Northern California. It took a team. There were 6 of us, including the students. We primarily used the students to carry the heavy stuff in, because we were having to go into some pretty remote areas and pick out areas and do some flight planning and optimization of those plans, including for large areas having to put visual observers out so that we could be compliant in several areas. I'll talk some about the software and how we got this. It's really a continuation. Jonathan had come out here with a team to Hot Springs to Magnet Cove, and we had spent some time. We already had a background of what it is we needed to do to make this happen. We'd already, at this point, eliminated 4 other pieces of software that didn't do what we needed, and so this was really a continuation. So how to put the platform, we already kind of had a plan that we had tried before, using some extended gear, basically cages and some tethers for those, how we would mount those. The aeronautical considerations are really simply this. Every time that you do this, it's unlike, I fly a manned aircraft. They hand me the manual. I can look at the where the envelope is for my center of gravity. I know when I put everything there how it goes. Now, I'm modifying something that has no data anywhere like this. I'm modifying it, and then on top of that, the center of gravity in this case, because the sensor had to be separated from all the electronics because of the magnetic field, I'm lowering it, and it's shifting all the time. So in the manned world, this would be the kind of thing that you would say, no, I'm not doing this, because it's just too many things. We now, based on the things that we now teach in our graduate course, teach students how to mitigate those so that they can do it. So we'll talk about the flight characteristics, and also control considerations in emergency operations. Here's the interesting thing that you don't have in manned aircraft, and that is unmanned vehicles like to fly away sometimes. So without command, and you have to have an emergency procedure, how you program them ahead of time, and then also how you control them when they come back. And I'll talk some about that with a couple of pictures that I've got to explain. So we had two sensors, the MagDrone and the MagAero. Like I said, the tether or the cage and the center of gravity issues that were differently. Here's something that was really, and we've recorded all this so that we have a way to replicate not just how the sensor data is done, but how the actual data is collected. So what we use with the drone, how it's flown, what kind of speeds we got to. We actually got to speeds, we tested speeds on this one consistently at 12.5 meters a second, which exceeds really what you would think you could do. It's very important because of battery life, which is the number one consideration when you're trying to use something of a drone this size. But we did short spurts for 14. So what that meant was we were basically able to gather nearly twice as much data in the same amount of time on the same battery as had been done previously because we were able to test while they were there. The big constraint we had was that they're within an envelope and a range. USGS said they wanted this to be a consistent height above terrain. So we had to find a piece of software that would terrain follow. So we obtained DEMs, and UGCS is the only one that does it. We had tried some others and tried to trick it. This is the only one. The great news about this one is from the time of Magnet Cove until this, we found all the things we didn't like about that software. I talked to the vendor when we were at the vendor show, AUVSI, the big show in the spring. Plus, we had given feedback, and they fixed nearly everything that we needed. So by the time we did this, with some very difficult terrain following, we were able to do this even at high speeds, and they had made the changes that we were having to do manually before that was very difficult. This is exactly what we teach our students. You look at this, you do a risk assessment, and you look at it. In this particular case, none of our students would ever be able to mitigate it enough because it's based on experience, a lot of it. And so when you get to how much time you have, they wouldn't get there. But we mitigated each of those down so that we could effectively do it. We did have an IMU confusion error. I'll talk to in a minute when we look at the way that we mounted this. But here's where you do get everybody appreciating it. When you've spent $100,000 on a sensor, you like us going through this part. Because if it crashes, often the sensor doesn't do too well. So we spend a lot of time testing, simulating the sensor real time before we ever actually put it onto the UAS. And then we do an airworthiness test card each time. Same thing we train all of our students to do, and we test them on here in the courses, that they're going to do it, they're going to test it, they're going to make sure that it acts as you would expect it. Sometimes it doesn't. We've had some uncontrolled oscillations that have occurred with some things in design, and then we had a harmonics issue this time that was a very interesting thing that we're actually going to write up to try to figure out. Okay, here's a picture of the cage with the MagDrone. If you look here, you'll see the yellow connectors. So the yellow connectors on the arm that connect the cage. Really what we've done is trick it, disabled the landing gear so that we can get that separation with the cage. On this particular one, we did this before, printed those. They're custom made on the 3D printer here that we did in the engineering lab. But we printed them with a lower density piece of material. And we didn't have any issues with any harmonization. We put this on, and every time in the first few flights we did, we started to get a harmonization issue. And by that I meant we had some violent bouncing at the ends. Now you can look at it, and some engineers here would look at this and go, oh, yeah, I can see how that could happen, because as soon as you get into ground effect, you can no longer have the arms absorb what's going on. And so as soon as it got into ground effect, it started having some harmonization bouncing around, and actually flipped over once in trying to land on one of them. We had to do a repair. So we went back, re-looked at this, even though it was identical, moved some things and adjusted it, and then we were able to make it work so that we could fly, and we minimized what was going on with the harmonization. This is the mag area. So it's on a tether. We fly that, and it did a great job. We were able to fly. This is the one that we got 12.5 meters a second consistently, 14 meters a second, covered large areas, flying it out right at the edge of our visual line of sight to be legal, over 2 kilometers, about 2.5 kilometers that we got to. We extended with some visual observers to do that, and the data that was collected, we had, so those of you that are involved in this kind of work, in that 8 days of, this includes the day that we lost for having to do a repair while we were there, we had actual flying time was about 25 hours. So if you've ever done this kind of stuff, you know that's a lot of flying. That's a crazy amount of flying for drones in that amount of time. We were flying, charging with generators, just one after the other, and then moving. Plus some places it took us over an hour over rough terrain to get there and launch. This is the area. You can see generally what it looks like and what we were dealing with terrain-wise. It was pretty challenging. The terrain following was definitely challenging, but even the flight planning, spent a lot of time on flight plan optimizations and where we were actually going to place people. Interesting, you know, we figured out here before we left, you'd think that we would have thought of this. We looked out at the visual line of sight and said, we're pretty sure that we can do this past 2 kilometers. We did several tests out at the farm, done it in several different conditions, and said, yep, we can do it. But at 400 feet and 2 kilometers, it's going to go below the horizon and I'm not going to be able to see it. So we had to plan then and go back out and find some high ground, and with ATVs, sent visual observers out and had contact, and we were able to complete the missions that way. Here's the one that's most, so this tells you on field work when you do it, you have to come up with these unique things. So this particular outcrop, you can see here, we were launching from down there. We had to fly over these peaks, which were about 30 meters, and we were flying, so we could only get to this one side to launch, had to fly across. We couldn't stay there though, because you have this thing about line of sight with the remote control, and as soon as it loses it for more than 2 minutes, it's going to return to home and try to land. So I should have worked out a little bit beforehand, but the solution we ended up having to come up with was to launch and hover, and then I had to scale up this very steep on this side area with the controller to get to the top, to then take control, initiate the flight plan, and launch it to go back and forth. And that was the only reason that we were able to do it was because of a new modification using the tablet only. Very challenging, but we did a lot of ground that we were able to cover in a very short period of time. So like I said, kind of the findings in future to talk about where we would be, and I use it, this just is a good case study about not just this project, but other ones where typically a researcher shows up and says, hey, could you help me with the compliance? And they've done a good job of picking out the sensor, but then they'll have a drone that won't work, or they'll have something else that doesn't fit, or they can't, it's non-compliant, they want to fly at 1,000 feet. I mean, they're on and on that we're trying to help them to get around. But out to 2.5 miles is a pretty significant, you figure the amount we were able to cover, and we optimized those plans to where it was working its way back towards us. If you get 20 to 25 minutes of battery, the time for that to run out is not when you're 2.5 kilometers away, it's when it's on the way back. And so we spent a lot of time making sure that we planned those the same way. The issues with UGCS worked out great too, by the way. They greatly improved that just in this 6 months. The aeronautical piece, the center of gravity, we've developed our own basic for the 600 when we moved that, basically our own, if you will, center of gravity envelope, just like I do on a manned aircraft, so that I know when it's below me that I can figure out what it's worth. Oddly enough, we'd hypothesized that the cage was going to give us the most problem, or rather the tethers were going to give us the most problem on the turns, especially at high speed and making turns when we developed some turns. But actually it was the opposite. The tethers were able to absorb the energy and allowed the drone to. The cage was very problematic. In fact, so problematic, Andy's working on a modification on the gear that we'll try when he gets back, but we'll probably will abandon the cage eventually, just because the aeronautical part of it's just too difficult to do. The issue on the harmonic vibration, that's one of the very significant issue that happened there. Really, it was a showstopper. It caused huge problems. IMU was getting confused. We were having to do constant IMU and compass calibrations to try to work. And then control and emergency operations, and here's one, and we're writing this up in the article. But on a return to home, so right now we're talking about how much tolerance we have and the accuracy required for navigation. So in the manned aircraft world, what we've always done on navigation is it's way out here until you get closer to the runway, right? And then it kind of funnels in and how much you have to have. And then, but then at the very end, it depends upon a human taking over, seeing the environment, and then landing manually. Now, we have some auto lands, but nonetheless, that's the general way. Really, autonomous vehicles, I mean, we could program this, it would take off, and it would go, and it would come back, and it would land, typically within a couple of meters of the same place. And so if you've cleared off a place like we did in the desert, it's great. However, when you're strapping things on it like we're doing, it does not do well. Cables get caught in props, it crashes, it can't operate that way. So we now have to revert to that same thing. Everything has to be takeoff manually and then land manually. And that is kind of changed, and that operation we put into a procedure that we use for those as well. Last thing I'll say is this, with their process, we have a night waiver, and that came out of a requirement that some had here on the university. We're in the last throes of a flight over people. I'm hoping by the first of the year we'll have a flight over people waiver. And if some of you think of research you're doing, the ability to not have to clear an area is a huge thing when you're trying to collect. And then beyond visual line of sight, that requires a little bit more investment, but nonetheless, that's going to be the next one that we get along with an airspace waiver that we already have. So, okay, that's all I got.
Thanks, Rick.